That's great. Mous, you are from Groningen?
Yes, I'm actually presenting instead of
okay,
this
great.
guy here on the right side, which is Mous.
Philip. Yeah.
And so I'm Philip myself. So this is one of my master students who actually did this work, and he also wrote a paper, but unfortunately he couldn't join the conference, so I presented his stead. So what we did, we got the question by the Dutch, which is the, let's say, the collaboration, international collaboration of the Dutch government with international governments, and they got a new INSAR data set run by the company Sensar for the cities of Semarang and Pekalongan in the north coast of Java. And they would like to have interpretation on that data set. So Tam actually went to Indonesia for fieldwork for several months, and he collected a lot of different data types, and he ran this analysis. So the introduction, okay, we talk about relative sea level rise, land subsidence. These two cities are located, as you will see in the next slide, in the north coast, at the coastline. And well, you can see on the right-hand picture, for example, a house. Well, it hasn't been constructed like this, as you can imagine, because you would completely bump your head when you walk in. So the whole house has sank very significantly since it's been built. And the aim of the research was to, first of all, unravel this new data set of PS INSAR and try to find out what could be the possible drivers of land subsidence and find, let's say, both spatial and temporal relationships here. Also with the aim to inform, let's say, decision making and management towards the future. So here we have the study area. So we go to Indonesia, to the island of Java. And we go to the east side, the central portion of Java, where we have Semarang and Pekalongan as two large cities. So we are on the same coastline of Jakarta, which is more to the west side, and also the same kind of subsurface composition as Jakarta. So here we see the PS INSAR for the two cities. And well, you clearly see these large areas of high rates, right, situated where we have these really warm colors. And they are on the same scale bars, and you can see that land subsidence rates, they go up to decimeters even if you are in this dark red colors. So it goes up to beyond almost 2 decimeters, 20 centimeters per year, which is huge if you consider that these are coastal cities. So first of all, let's unravel and unpick this INSAR that we have. Look at the distribution, the extremes, the seasonality, and also some urban differential subsidence using buildings as natural extensometers. So let's look at the land subsidence rates. So for on the left hand Semarang, rates go up to staggering 18 centimeters per year. In Pekalongan even reach 20 centimeters per year. And cumulative land subsidence is over a meter, and this time series is approximately 4.5 years. So when Tam started unraveling this, he looked at the seasonality signal within his INSAR. So the PS points, they neatly actually follow these different seasons, right? The wet season, dry season, and there is this high connection to seasonality that we see clearly from here. So this is, of course, very important to realize when you have singular points of measurement in time, and it's been highlighted in other talks as well, right? That you have to account for that seasonality in your system. So another analysis was looking at several large buildings that were in the cities, and what we tried to unravel here is, could we see a difference between the founded or expectedly founded large buildings and the surroundings? And therefore we selected really the high-rise, let's say local high-rise buildings that were there. So we could see if there's any depth information that we could derive from there. But actually what he found is that most of the buildings, they didn't actually show a lot of difference with the surroundings, so the streets around it. So it actually gave us an information that the majority of this land subsidence actually happened deeper than the shallow part of the foundations, which is well opposite to many of the other cases that we see. And this is actually an important finding because, oh, sorry, went too fast. Because in an earlier report, just a while ago, there was, it was actually a Dutch consultant, but a consultancy firm, and they wrote down that the majority of land subsidence is shallow. But of course, as you can imagine, if that's the case, your whole mitigation strategy is completely different than if it's deeply sourced. So with this analysis, we could basically debunk that first assessment in which they didn't have this data at hand. So another thing, spatial correlation with geological layers. So TAR managed to get geological maps and run that. We also managed to get a time series of geodetic benchmarks from local agencies, which is great data, hard to get, but we did that anyways. And land use, land cover maps, and change maps over time. So let's see what comes out. So here we see several of the geodetic points. In total, there was 25, and actually most of them very neatly follow. And so these are the blue dots that we see here. They actually neatly follow also the same trend as we see with the PS INSAR in there. So there's a great correspondence to them. There's a few who are a bit less connected, and we plotted here 2 examples of let's say the worst, the least performing benchmarks. I mean, the trend is in the same direction, but of course there's some absolute values difference. But most of them are in correspondence, so that gives us trust in the quality of the INSAR. If we then look at the spatial distribution of geology versus land subsidence, there's a very strong link to unconsolidated deposits, as I think all of you in the room can also expect if you had to guess. But most of the old deposits, the consolidated, right, the bedrock outcrops, they're the ones who are almost completely stable, and we see most of actually all the action happening in these coastal deposits and these alluvial fens. So here we see a connection with the land cover and land cover change. And here something different happens for both cities. So if you look on the left, Pekalongan, there we neatly see a connection between anthropogenic land uses. So these are the build-up areas, but these are also the agriculture areas versus the natural land use classes. And this is only all for the unconsolidated setting. So we exclude the geological influences from this analysis. So here it actually follows what you would expect, that more anthropogenic influence causes more land subsidence. For Semarang, actually this is not clear. There's no clear distinction between these land use classes. And actually one of the, what we suspect is happening here, that there's a lot of mixture between, let's say, what is classified as natural land use and what is classified as agriculture, different agricultural classes. And they're very patchy, very close to each other. So basically the hydrological system potentially driving the land subsidence is affecting both classes. So we see a mixed signal. So let's move to the final conclusions then. So we see this seasonality that really depend on the hydrogeological fluctuations in the system. Well, the compaction seems to happen, and this is, I think, one of the very big finding that here, that below this foundation depth of buildings, and this is really what before was communicated at least to the local authorities differently. It appears, I would say, almost, of course, on these unconsolidated alluvial plains, as we also know from Jakarta, of course. And it connects, especially for Pekalongan, with urbanization and cultivation of the land. And then if we go back, for example, to these rates that we see, right? So we talk about 10, 20 centimeters a year. So these cities are now sinking at the rates that Jakarta used to sink at its highest peak. So we are basically looking at some of the fastest subsiding coastal cities, I think, that we have at present around the world. So it's a major urgency to actually focus on what can be done. And there's a poster on TISOLS here that actually looks in the socioeconomic frameworks on how to actually reduce and try to mitigate that. And also appreciate the photo on the right side. There was a breach in the seawall in Semarang, and well, the whole district flooded. And this picture was actually taken a few days after the breach. So even after the breach, the whole city was still full of water. They don't have an effective pumping system to get the water out. So this is majorly disrupting the life in the city, as you can imagine. With that, I'd like to thank you.
impressive topic.
Thanks.
Really, thanks. I suppose that there will be a lot of questions.
Thank you for the talk. I was curious about the land use differences with regard to the PS INSAR. The results you were showing. I guess the question is, how confident are you that this is a real result as opposed to coming from the difference in the number of PS and the quality of PS pixels in these two land uses? And I wondered if you have different, if you had your geodetic reference points, both in the anthropogenic and the natural terrains, to give you that confidence.
I think on this one we're actually pretty confident in these results because there's a clear distinction, especially for the Pekalongan case. You can really see this big, let's say, land subsidence ball taking place in the city, right? And it spreads out to the fringes of the city, and then it basically flattens out when you reach the natural areas at the coastline around it. And in Semarang, well, there's really this mixture between these classes, and therefore I think it's on a small, let's say, spatial scale, while, let's say, the main driver, of course, of this land subsidence here is extraction of groundwater happening at a bigger spatial scale. So you may extract from one point, right? You have a shrimp farmer somewhere, but of course the impact of that extraction, it may span out for, let's say, a whole radius around that single farm that also may affect your natural land use classes there. So we haven't looked at specific benchmarks in different classes, but we were pretty confident that that this analysis is actually quite robust. Yes.
Small follow-up, if I may. Do you have lots of PS pixels in the natural terrain? I can imagine there'd be fewer reflectors there.
There is. I'm not sure the exact amount, but we've excluded, let's say, the classes which have only few pixels. And so also in these natural domains, there are like things like roads or small things that do give us some PS reflectors. But yeah, you're right. That's of course something to consider if you want to go into depth. Yeah. Thanks.
Thank you. One more question?
Thanks. That's a great question. Unfortunately, I cannot give you a great answer to that because we are still, let's say, we don't have very accurate geological data on boreholes and layering, unfortunately. So yeah, to answer that, and I think, I mean, it's not a nice, let's say, stack of aquifers and aquitars as we know from other systems. Maybe it's really a quite messy, I would say, alluvial fan deposit. So it has very lot of pockets of sand and silts and clay. So there is permeability because we see the hydraulic heads moving up and down with seasonality. So also I think that the distinction between shallow and low is very gradual through that alluvial fan. Yeah. So that may be different from your case, and you see that.
I have a very small related question because I was really curious about something. You started your presentation with that the student went to Indonesia for several months to collect data. So I expected a lot of subsurface information, actually, corings, etc. But what did he collect actually?
Yeah, I mean, we hope that we also get those kind of corings. Now, so basically all the other data. So some of it is remote sensed. Okay, we could get that from afar. But for example, the geodetic benchmarks is from there. We also have, didn't show it here, but some piezometric levels measurements. They installed some actual benchmarks. Let's say land subsidence extensometers. Weirdly enough, they show 0 subsidence in the depth domain. So we suspect that there's something fishy going on in the observations with these monitoring benchmarks, because they would actually suggest, if you trust those results, that there will be 0 compaction happening in the first 100 meters. And that is a bit hard to believe if you are in a setting like that. So we suspect that there's something going on in the way they are just monitoring their own benchmark. So okay, we communicated that to them, of course. Yeah. So those kind of data were mainly what we could find. Archive data and yeah.
Thanks for your talk. Really interesting. So it sounds like what you're saying is that the land use type is more continuous in Pekalongan, where you have like large areas of irrigated crops and things. So if there's pumping there, then there's head declines there, but it's not propagating into the natural areas. Whereas in Semarang, they're smaller. Like you might have a very small irrigated area right next to a small natural area. Is that correct?
Yeah, correct.
Okay. And that's from the land use data you have that backs that up, I assume.
Yes, it's really you can imagine the Semarang case. Can we see it if we go this, just to give you a quick idea. So in this area right here, you also see a reduction of the amount of scatterers, right? But this area is an area where there's a lot of, there's no big cities, but there's like communities, farming communities. More and more they turn to shrimp farming simply because the sea is encroaching and they're losing all the land. But it used to be a connected plain, so this used to be the coastline right here. So already there's really villages being completely deserted and sinking and eaten up by the sea in this region. So it's small scale, let's say, farming, but extracting a lot of the groundwater, which isn't recharged at the same rate. Yeah.
Okay. And you have some piezometric data as well, you said?
Yes, very messy, and that's why we didn't put in very messy, scattered, let's say, measurements.
And probably not time series, or do you?
It's well, not really. So it is some points over time.
Yeah.
What we do see is that the heads are let's say, really low below surface. So they can be tens of meters below land surface because of the over extraction.
Thank you. Thank you one more time.